Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the generalized entropy departure chart. The entropy change of a real gas is determined by following an approach similar to that used above for the entropy change. There is some difference in derivation, however, owing to the dependence of the ideal gas entropy on pressure as well as the temperature. From the second equation of ds, equation 532, with T and P as natural variables, we have the thought that comes to mind at this point is to perform the integrations in the previous equation first along a constant temperature line to zero pressure, then along the constant pressure line to a constant pressure, and finally along the constant temperature line to the pressure, as we did for the enthalpy. This approach is not suitable for entropy change calculations, however, since it involves the value of entropy at zero pressure, which is infinity. We can avoid this difficulty by choosing a different path between the two states, as shown in the following figure. An alternative process path to evaluate the entropy changes of real gases during process 1 to 2 is this path: 1 to A asterisk, to 1 asterisk, to 2 asterisk, to B asterisk, and to 2, as shown in the figure. Then the entropy change can be expressed as states 1 and 1 asterisk are identical, and so are states 2 and 2 asterisk. The gas is assumed to behave as an ideal gas at the imaginary states 1 asterisk and 2 asterisk, as well as at the states between the two. Therefore, the entropy change during process 1 asterisk to 2 asterisk can be determined from the entropy change relations for ideal gases. The calculation of entropy change between an actual state and the corresponding imaginary ideal gas state is more involved, however, and requires the use of generalized entropy departure charts as explained below. Consider a gas at a pressure P and temperature T to determine how much different the entropy of this gas would be if it were an ideal gas at the same temperature and pressure. We consider an isothermal process from the actual state Pt to zero pressure and back to the imaginary ideal gas state P asterisk T asterisk, as shown in the figure. The entropy change during this isothermal process can be expressed as, where V is expressed by this relation, V equals Z RGT over P, and V asterisk is expressed by this relation, V asterisk equals V ideal equals RGT over P. Performing the differentiations and rearranging, we obtain. By substituting T and P and rearranging, the entropy departure can be expressed in a non-dimensionalized form as the last term is related to the entropy departure, which have been determined. The difference S0 minus S is called the entropy departure, and Zs is called the entropy departure factor. The integral in the preceding equation can be performed by using data from the compressibility charts. The values of Zs are presented in graphical form as a function of PR and TR in figures B8. This graph is called the generalized entropy departure chart, and it is used to determine the deviation of the entropy of a gas at a given P and T from the entropy of an ideal gas at the same P and T. Therefore, the entropy change of a gas during a process 1 to 2s, where the values of Zs or minus Sr are determined from the generalized entropy departure chart, and the entropy changes S2 minus S1 ideal is determined from the ideal gas relations for entropy change. Notice that the last term on the right-hand side is 0 for an ideal gas. Okay, that's all for this task. Thank you very much, and see you next time.